Okay, so in this lecture, let's go ahead and jump into the Stille reaction. And this is when your metal is tin. Okay, so it looks very similar to the Suzuki reaction. We need an aryl vinyl um, alkyl halide or triflate. Remember, tin is right beneath carbon and silicon, so it can hold four things. So tin is bonded to the substituent that we want to exchange in our transmetallation step, and three ligands, and we'll talk about those ligands in a second, just like we did with the hydroboration. We typically have our palladium catalyst, and in this case, we do not need an additive or a base. And just like before, we have the coupling of our R groups. And we typically are forming carbon sp2, carbon sp2 bonds. In certain cases, we're forming carbon sp, carbon sp2 bonds. Rarely are we forming carbon sp3 systems, and we'll talk about why in a second. Okay. And so the mechanism is pretty straightforward. I'll go into this tin reagent in a second. It's a lot more straightforward than the boron Suzuki reaction. So let me talk about the mechanism first. It's just three steps: oxidative addition, transmetallation, reductive elimination. Again, very similar to the Suzuki reaction. If you start off with your palladium triphenylphosphine, your first step is oxidative addition. Okay. Now, in this case, there's no side reaction that's occurring. The tin reagent that we have is set to insert itself into the reaction and proceed through the transmetallation step. And so, again, there's no side reaction. It's just straight into the transmetallation step, where again, you're exchanging of ligands. So now my halogen or my triflate that's bonded to my palladium is bonded to my tin reagent. And my alkyl group that was once bonded to my tin is now bonded to my palladium. And you've got your reductive elimination step, where you form your R1, R2 bond. Okay. And so before I go into another example, let me talk about this tin reagent. Okay. Um, Typically, the L groups, i.e. the ligands on the tin, are methyl or butyl, i.e. alkyl groups. And that's really just because these alkyl groups and tin are forming such a strong bond. Now, the R2 group that gets transmetallated or transferred onto the palladium are typically triple bonds. Let me write this out and move it over here. And the reason I just moved it is because triple bonds are um, faster to transfer to the palladium. Followed by double bonds, followed by aryl groups, and allyl and benzyl, and finally, alkyl groups are the worst. And again, the reason for that is because your alkyl groups are forming a much stronger bond to tin as opposed to your triple and double bonds or aryl groups. They're weaker bonds, and so they're transferring a lot faster to your palladium. Okay, so it makes sense that if the alkyl groups are the slowest to transfer, then my ligands, right, to satisfy that octet rule, are alkyl groups. They won't transfer as fast as a triple bond or a double bond. Okay, so let me give you an example of this reaction, but an actual example with alkyl groups or vinyl groups, aryl groups, triple bonds, excuse me. And I won't stay too long on the Stille reaction because it looks very similar to the Suzuki reaction. But I do want to give you an example and then talk just briefly about the Suzuki. So just like before, for our mechanism, we start with our palladium catalyst. But just like before, it's a cyclic catalytic reaction. So you have to regenerate your catalyst. It's cyclic. You have to come back to your catalyst. And like I mentioned before, your first step is an oxidative addition step. So you introduce, in this case, your vinyl bromide. I'll just write tert-butyl. Oxidative addition. As I previously mentioned, your tin reagent is already set up. It doesn't have to be prepped. So you can see that it's the triple bond that's going to transmetallate. If you need to number the carbons, by all means, number the carbons. There are 4 atoms. The triple bond is between carbon 1 and 2. And you're swapping the halogen and, of course, the triple bond, so that now your palladium not only has the vinyl group, but the triple bond system. And again, the last step is reductive elimination. Where you're regenerating your catalyst, and the carbon 1 on the alkyne and the vinyl carbon are the ones that are bonding to each other. Those are the ones that are coupling. That's the new bond. Okay. And in this case, you formed a carbon sp2, carbon sp bond. So this is a pretty popular reaction. Now, typically, the Suzuki is the most popular of the 3, and it's the most popular of the 3 because it's the easiest to work with. The HEC, as I just mentioned, can do beta hydride eliminations, walk the double bonds down a chain if your chain is super long. The problem with the Stille reaction, and the reason why I'm not staying on this reaction so long is one, the mechanism looks really similar to the Suzuki. It's a lot easier than the Suzuki. But the problem with this reaction is that you're using tin, and tin is toxic. And so when you run this reaction, the waste that comes with it is really hard to dispose, and no one wants to deal with all of that. And so the easiest reaction to follow through with is the Suzuki reaction. So again, its real only downfall is the toxicity of our tin or our stannate system. Okay. Okay, so now let me go ahead and jump into reaction number 4, which is, or reaction number 3, excuse me, reaction number 3, which is the Sonogashira Castro Stevens reaction. And again, I'll come back to the Suzuki and the Stille, but I just want to give you a general overview of these reactions. Okay, so the Castro-Stevens reaction is very similar to the Heck in the sense that you have an aryl vinyl alkyl halide or triflate, and you have a pi system. In this case, your pi system is an alkyne. You add your palladium catalyst. Okay. Now, in this case, not only do you need a base, just like in the Heck reaction, and not only do you need a pi bond, just like in the Heck reaction, but you also must have a copper 1 salt. So typically it's copper bromide, copper chloride, or copper iodide. Okay. And so this is really what's so different from the Heck reaction and the fact that your pi bond is a triple bond as opposed to a double bond. But the product is the replacing of a hydrogen, just like in the Heck reaction. Okay. And so let's go ahead and talk about the mechanism of this reaction and the base and the copper salts. So we just talked about these copper 1 salts, right? And they're copper 1 because their anion is a -1. The base that's typically used for this reaction is an amine base, and we've seen a ton of amine bases with the oxazolidinones and the thiol systems, the pseudoephedrins. Yeah. Okay. So that's the base that's pretty popular, are amine bases. And let's jump into the reaction. And we'll talk about the reaction as we're moving along. So just like before, you start with an oxidative addition step and you end with a reductive elimination step. Your middle step is a transmetallation. It's 3 steps. Okay. Now, not surprisingly, you just can't add your alkyne, right? It doesn't have a metal on it. So you need to prep it, just like we did in the Suzuki reaction. And so there's a side reaction that's occurring. Okay. And so this side reaction is taking the alkyne that you've got treating it with your base, your amine base. Now, you learned in first semester organic chemistry that alkynes, specifically terminal alkynes, and only terminal alkynes, because internal alkynes don't have hydrogens on them, right? Terminal alkynes are acidic, and they're acidic because you're forming a negative charge on a carbon sp, right? Because of its large S character, it's holding that negative charge really close to its nucleus, making that hydrogen incredibly acidic. And so because this alkyne is acidic, you formed its conjugate base, which then you can treat with your copper bromide or copper halide salt. And now your copper and your carbon are bonded. It's a ligand exchange. And the bromide is now counterbalancing the conjugate acid that you made. Now I can go ahead and now I can add in this specific reagent into my transmetallation step. So the side reaction is a little bit more cumbersome than in the Suzuki, right? You have to deprotonate the terminal alkyne. And once you deprotonate, you form your carb anion, which you then treat with your copper 1 salt, your copper halide to exchange ligands. And now your copper is bonded to your alkyne carbon that's now ready and set up to do a transmetallation. Okay. Once it's set up to do the transmetallation, again, you are exchanging the halogen. So not surprisingly, the halogen is now bonded to your copper. So you're regenerating your copper 1 salt. And now your alkyne is bonded to your palladium. That looks like it's coming out of my bond as opposed to my palladium. And just like before, the carbons that are bonded to the palladium are the ones that couple via a reductive elimination step. And we're done. So in this case, we need an alkyne. You have to have an alkyne. And not just any alkyne, you need a terminal alkyne because internal alkynes have no hydrogens. And the base is there to deprotonate that hydrogen on the alkyne. Okay? So just really briefly, Dr. Spence uses this reaction to form a lot of his starting materials. So let me just give you an example of what Dr. Spence does. This is from his JOC paper in 2006. And he actually starts with a dihalide system. And dipea, if you remember, dipea is diisopropylamine. And the following alkyne. And so, not surprisingly, this reaction occurs twice because I've got two halogens, right? Again, notice how this is a terminal alkyne. Okay. Just as before, let me try to go through the mechanism briefly or quickly, even though there's two halogens on there. The reaction goes through two cycles, right? It's not all happening at once. It does its first oxidative addition. So the mechanism is incredibly similar to what we just talked about. Our side reaction is the terminal alkyne, where instead of a CH3 group, he has a TMS group. He treats it with his dipea base, deprotonates, treats it with, sorry, he used copper bromide. Treats it with copper bromide. So now the Br minus is counterbalancing the conjugate base that we just made. And our copper is now bonded to our alkyne. And when I say bonded, I mean ionically bonded, right? Because it's still a copper, it's still a metal, right? And now it can proceed through its transmetallation step. And in this case, you form the copper 1 iodide salt, and the palladium is now bonded to my alkyne. And it does a reductive elimination step to regenerate not only my catalyst, but to couple the first alkyne. And it goes through another cycle because there's another halogen. And so your second cycle oxidative addition with one of the alkynes already present. And again, I'm not going to go through the side reaction again, but it's same as above. I do my transmetallation step. And again, I form more copper iodide, so copper 1 salt. And finally, of course, my reductive elimination step. Mhm. And so this is the starting material that he wants to make because he does a Bergman cyclization which I'm not going to get into it, to form a six-membered ring, an aromatic six-membered ring with substituents. And so you can see that it's set up really nicely to have six carbons and to form a six-membered ring system. But it's really nicely done how he gets his starting material through the Sonogashira Castro-Stevens mechanism. Okay, so those are the three reactions that I wanted to discuss. In the next video, what I'll do is I'm going to go back to them, but we're going to add more to the mechanism. Okay.